Hi everybody, we are going to start with scientific notation 11.1.4. We're going to do the first part of this, so I'm going to call this scientific notation part 1. And so that'll be the first 2 or 3 pages of the notes packet, and then we'll finish up with part 2 on a different video, just so the video doesn't get too long on this one. So scientific notation applies what we just learned about exponential notation. And so that's going to be great because it's going to be an application piece that we're going to use off the rules that we just learned. It can also be useful in expressing extremely large or extremely small numbers. It can also be useful when we are computing very large numbers. Because sometimes, like even in the very basic calculators that I've checked out to you guys, we can't punch in more than 10 digits in, well, more than 9 digits in our screen. But if we put it in scientific notation, we can compute really large numbers because we're putting it in scientific notation. So for example, we're not going to go into the why yet because that's coming in the lesson. But for example, if we were talking about how fast light travels, and instead of having to write out that very large number every single time, instead we could just write it as 5.88 times 10 to the 12th miles. And so it would be a much kind of smaller condensed number to write. In the same kind of token, we can talk about how small something is. And so in this case, we're talking about the diameter of a hydrogen atom. So don't forget diameter. It's a chord of a circle. It goes right through the center of the circle. And the diameter of a hydrogen atom in scientific notation, we would write that as 5 times 10 to the negative 8 millimeters. And so we have that as our answer, putting it in scientific notation. So our scientific notation format, it says, when a number is written in scientific notation, the exponent tells you if the term is a large or a small number. That is an M. I'm having a little bit of a delay problem with the smartboard writing, and it's showing up. So the exponent's going to tell us a little bit about the size of the number, because if the number is very large, our exponent will be positive. If the exponent is negative, we're talking about a very small number. And so that's what we're going to write in here. A positive exponent indicates a large number, and a negative exponent indicates a small number that is between 0 and 1. So we have just kind of our definition here of how we're going to write it. A number is written in scientific notation when it is written in the following format. So we have m times n to the n, such that, so that gives us a qualification, such that m is going to be less than or equal to 1, or I'm sorry, m is going to be greater than or equal to 1, and less than 10. So m times 10 to the n, such that 1 is less than or equal to m, which is going to be less than 10. And n is any integer. There's that term integer again. So any positive or negative whole number is what that integer is. And then you may not have heard this term before. The m, and this is what I'm going to be using quite a lot here. The m is called your mantissa. So we're going to write that in. Mantissa for that. All right, so converting decimal notation to scientific notation, we are going to move the decimal point to the left until you get a number m such that 1 is less than or equal to m, which is going to be less than 10. And this is going to be your mantissa. So here, this one was a freebie. So that one's already filled in for you. So this is going to be your mantissa. And then our next step is going to be next, count how many places you move the decimal point. The number of places moved will be a positive integer, n, and it'll also be the power of 10 in your scientific notation. And then in the parentheses, it says, note, moving the decimal point in step 1 changes the value of the number. Therefore, you're going to have to multiply the mantissa by a power of 10. That will result in the same number you started with. Right? That makes sense. If we are messing with one part of the number over here, and we're essentially dividing it by a certain power of 10, we've got to take the other part of the number and multiply it by that same power of 10 so that we're talking about the same number. That's what that note is talking about. All right, so we're gonna try those steps, these steps here in these examples. So 180,000. So I'm gonna read my notes from my paper so that you're following along on the steps. And so we've got this number, and it says move the decimal point to the left until you get a number m that's in between 1 and 10, right? So you're looking, our decimal point in this number is right here. So we're going to move it over 1, 2, 3, 4, 5. And why did I stop there? Why didn't I stop after the 8? So you should answer that question. Why did I not stop after the 8? Because if I stopped after the 8, we would be talking about the number 18 times 10 to the 4th power, but 18 is not in between 1 and 10. So I have to keep going another space until what I would have is 1.8. So I'm going to have 1.8 times 10, and then you count how many spaces we move. So 1, 2, 3, 4, 5 times 10 to the 5th. And because we started with a larger number, that integer, the integer value on the power of 10 is going to be positive, right? So instead of like, if we had started with a very small number here, the sign on my exponent would have been negative. But because we're starting with a large number, that exponent's going to be positive. So on this next one, you're going to have to think about how many spaces am I going to move my decimal over so that my mantissa is in between 1 and 10. So do it. Here we go. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is my count. I'm going to write that down so I don't forget as I get ready to talk. I know some students have been tempted to stop before, after the 4, or in between the 3 and the 4, or after the 9. Again, the question is, you need to find a number that's in between 1 and 10 that's going to be your mantissa. And so for this one, we would have 1.9000034 times 10 to the 14th. And then in this case, this might be one of those numbers, I'm not sure. I'm not sure that this number makes sense to write it in scientific notation, right? I'm not sure that it's much smaller or much simpler than writing out the big long number. So those are things you have to think about, like if ever you're writing a scientific paper, to think about which one makes more sense to express my answer. All right, so now we're going to go the other way. I want you to see that up here, the directions were to write an extremely large number and to convert it into scientific notation. Well, now we're going to take an extremely small number and then we're converting that into scientific notation. So that's going to be the steps we're going to fill in here. So it says, move the decimal point to the right this time until you get a number m such that, same rules apply, 1 is less than or equal to m, which is going to be less than 10. So it's still going to be in between 1 and 10. And this is going to be your, it's not a freebie this time, your mantissa. So that's going to be your mantissa. Next, you're supposed to count how many places you move the decimal point, the number of places moved will be a negative integer. So this time it's going to be negative, not positive. And it's also going to be the power of 10. In your scientific notation. And so again, you have that same note. Moving the decimal point in step 1 changes the value of the number. And so it's that same note that was on the previous page. So we're going to apply those rules to this example. And again, we're going to keep going until the number that we create is in between 1 and 10. So we keep going. 1, 2, 3, 4, 5, 6, 7. And my question too is, do I stop at 7? Or do I keep going one more? Do I keep going 2 more until it's 803.2? And again, go back to your definition. That mantissa has to be in between 1 and 10. So if I write it down right now, it would be 8.032. Is that in between 1 and 10? Yeah. So we can write it like that. So it's going to be 8.032 times 10. What was that? To the negative 7? Yes. To the negative 7, keeping myself from having to count again. So we've got negative 7. Again, it's negative because we started out with a very small number, and in order to get back to that very small number, we would be dividing by 10 to the 7th power, right? Which is going to be 10 to the negative 7. All right, so that's our answer. So then what I would like you to do in a face-to-face class, I normally have you guys do these problems as like a little group activity with your table buddy. And so what I want you to do is try to do these. I'm going to do the first one with you as we read the directions. It says, determine if the following numbers are written in scientific notation. If not, circle the error or errors and correct them. So we have this first number, and here is what this person wrote in as their number in scientific notation. And so you're supposed to assess it. Is this correctly written? Yes or no? And if not, what is the problem with this one? So if I'm you, I'd be looking at this number over here and saying, well, let's just write it in scientific notation. So I would have put the point here, and I'd go 1, 2, 3, 4, 5, 6, 7, 8. So it'd be times 10 to the 8th. That part looks good. What about the mantissa? So the mantissa looks pretty good, but it's not fully correct. So you can't just chop off the other part of it unless it tells you to like round to the hundredths place in the directions. And it does not tell us that. So what it should have been written as is 5.430008 times 10 to the 8th. And so then that's the correction that needs to be done. So if I was you, you are circling the error, which is the mantissa, and then you are correcting it on the right-hand column. So what I would like for you guys to do is complete these examples here, and then you guys can ask me about them in class because I'm going to be checking it to make sure that you guys did it. So if you have any questions, you guys can come ask me during office hours or check in with the Learning Center too. All right. So the next part of the notes, we've got converting scientific notation to decimal notation. And so we're just going the other way. So it says, move the decimal point the same number of places as the exponent. If the exponent is positive, move the decimal point to the right. If the exponent is negative, move the decimal point to the left, which I'm sure you all guessed. All right, so here we go. So example number 1, if we've got 5.21 times 10 to the 5th, what I would tell you to do is rewrite the 5.21 down below. Give yourself some space off to the right over here. And then we're going to be moving it, because this is positive, we're going to be moving it 5 places to the right, because that's this rule, right? So we're going to go 1, 2, 3, 4, 5. So the decimal point moves back here. We're going to fill in zeros in these spaces, and it's going to be 500 921,000. And that's going to be our answer. So let's try a couple more. So our next one is if we have 9.6001 times 10 to the negative 6. So again, I would take your mantissa and rewrite it down here, this time giving you some space to the left. So over on this direction, because that's the way we're going to move our decimal, right? Because it's negative, we're going to be moving it to the left. So it's going to be 1, 2, 3, 4, 5, 6. The decimal moves way over here. We're filling in zeros for each of these. So we've got 5 zeros. And so your answer ends up being 0.00000960001. And that's your answer. And then one more. One more for you. If we have negative 1.01 times 10 to the negative 4th, again, leave yourself some space again to the left. And we are going to take, and I'm just going to forget my negative just for a second. And then I'm going to go 1, 2, 3, 4. Move it over here, fill in these 3 zeros, and then I know my answer is going to be negative because that's what it started out being, was negative. So then my answer is going to be negative 0.000101. And that is your final answer for that one. All right, so that's the end of kind of part 1, and part 2 is going to come in the next video. Thanks for tuning in.